In this video lesson, I would like to solve a galvanic cell problem, but before we do that, I want to do a quick summary lesson about what a galvanic cell is and how it works. And then after we do the lesson, we'll look at a sample question from one of the older AP chemistry exams. So what is a galvanic cell? It's basically a device that converts chemical energy into electricity using redox reactions. So a redox reaction, remember, involves an oxidation in which electrons are lost in one reaction, and a reduction, which I'll just abbreviate here, in which electrons are gained in another reaction. And so if we can harness the movement of electrons, the ones that are lost to the ones that are gained, if we can kind of capture that movement through a galvanic cell or through like a wire, for example, then we've generated an electrical current, and that's electricity. So let's go over to our diagram with these beakers, and let's label this the anode over here. And the anode we're going to talk about, but the anode, I'm going to pick a metal, which is zinc. And zinc is a metal that actually gets more spontaneously oxidized. So there's a data table we can look up, but we can see that zinc is a metal that, yeah, it likes to actually be oxidized, or prefers to do that over the reduction. So here's the equation, the oxidation of zinc. So as we can see, it will break down or oxidize into zinc ions and 2 electrons. So I'm going to illustrate this on my diagram. So the zinc metal is oxidizing into zinc ions, which are going to float into that solution, and then electrons, 2 electrons here. Okay, so those electrons are going to be lost into the solution as well, so they're getting oxidized. And if I look at my note, it says that the anode, not only does it get oxidized, which I showed, it also loses mass. And hopefully you can tell that from my diagram. So here's my reactant, zinc, and if you look, it's constantly getting broken down. So over time, it'll just get smaller or lose mass as it's constantly getting broken down or oxidized to liberate these electrons. Okay, now let's draw actually a little wire to connect my electrodes. And on the other side, we're going to label this the cathode. And this is where the reduction will occur. So for this cathode, I'll just call this copper metal. And again, from my data table, I can look up a standard reduction potential. I see that copper ions, so Cu2+, they have a greater tendency to be reduced, especially when compared to zinc. So here's the reduction equation. Copper 2+ ions plus 2 electrons produces copper, the metal. So reduction will occur at the cathode as I illustrated there. And let's kind of look at this. And it says the cathode will gain mass. So here's the electrons that I oxidized, and they're going to flow back up this way. They're attracted to this metal conductor, the zinc. These arrows that I'm drawing represent the electron flow. And the electrons are going to continue to flow from one side to the other. They're going to flow down this metal, and then they're going to flow into this beaker. Now, in this beaker, I'm also going to have this copper 2+ ion, because that will get reduced. And when this reduction occurs, if you can see my product, I'm going to create copper solid. That's kind of a secondary thing that happens. So not only did I create electricity, I'm also creating a product here, which is copper. So I'm going to kind of draw that as this little additional strip on the existing cathode. It will kind of plate itself on as a product. Okay, so so actually gain mass. You're going to get more of it as the reaction goes. Now, one more thing about this galvanic cell before we do a sample question is that we have to have a salt bridge to keep the cell running and to keep the electrons flowing. Okay, so this little thing that I'm drawing here, this is a salt bridge. And the salt bridge's job is to keep the charge on each side kind of balanced. Because if we go back to the anode side, if these electrons continuously leave, okay, so it's constantly getting oxidized, but like leaving that beaker, you can see that it's going to build up. We're going to have too much positive charge by this zinc ion. Okay, these zinc ions, by the way, you're also going to get more and more of those. So this side on the anode, it's going to get too positive. So we're going to use negative ions that will kind of diffuse in here, and just to help keep that charge balanced and to kind of help also push those electrons continuously up as they can go through the cell. On the reduction side, what's going to happen is it will get these positive charges here, or these positive ions, they constantly get reduced, right? So we're actually, the positive charge is decreasing on the cathode side. And so we're going to use positive ions, or they're just going to naturally diffuse here onto the cathode side, which is going to help, again, help those electrons flow, help that charge attraction, and also to complete the circuit. Okay, now there's more we can actually talk about for galvanic cells, but we can save that for another video. So another example is we can calculate the cell potential, or E cell, which is the difference in energy from cathode to anode, or the potential difference, the voltage, but we'll save that for another lesson. So let's try a sample question here where this is from, like I said, one of the older AP exams. So we're given a little schematic diagram here, which is great. That's a galvanic cell. That should look familiar. And it's telling me that I have copper as an electrode and tin as an electrode. And I have to basically identify which electrode is the oxidation occurring. And so there's a hint in the question where it says that the copper electrode increases in mass and the tin electrode decreases in mass. So if you remember from what we talked about up here, the anode is the one that's going to lose mass. And the anode is losing mass because it's oxidizing. It's kind of decomposing, right? It's oxidizing into ions and electrons. So the tin. So let's answer part A. So we know actually the tin metal is oxidation. And we can try to kind of annotate the diagram. So here's my tin metal. The oxidation is going to produce tin ions. It's going to be 2+. I know it's 2+ because look at this compound, tin 2 nitrate. So look at the nomenclature, right? This little subscript 2 indicates it's the +2 charge. And as this oxidizes, it'll also give out 2 electrons. So remember, as this breaks down, it's slowly breaking down or oxidizing to produce tin ions and 2 electrons. So I'm going to try to explain my reasoning by showing the redox reaction. So tin is the oxidation because its mass decreases, and its mass decreases represented by this equation. Sorry, you can word this a bit better than I am, but I'm just trying to kind of think on the spot here, think out loud. So its mass is decreasing due to this equation, where we can see that the the tin solid is physically breaking down and oxidizing to liberate those electrons. And so therefore this is my anode. So this one's kind of backwards from what I drew because these electrons will travel up and the electron flow will be this way. And it's an open switch, but that's okay. We'll just pretend that they're flowing down, and they will be eventually accepted by the copper ions that are in the solution. And it's copper 2+ because I can tell from the nomenclature again of this aqueous solution. Okay, good. So in part B, as the mass of the tin decreases, where did it go? Well, again, look at my diagram, and I also illustrated it up here in our kind of generic sample 1. The mass of it, it's going into the aqueous solution, right? Because the tin is being oxidized and all of those products are going in here. They're going into the beaker. So if you look at my diagram and you can explain it or you can annotate the diagram, the mass or the ions produced will gather, or they will basically, they'll gather in the aqueous solution inside the beaker, inside the oxidation or anode beaker. Okay, so hopefully that helps you answer that one. Again, this is from, I believe, the 2014 exam. And there's one more we can do that's related to our review lesson. So we're shown the salt bridge, which, again, I talked about in the review. So I'm shown here an expanded diagram of the salt bridge, and it's telling me that the salt bridge is made of potassium nitrate. So I'm asked to draw and label a particle view of the salt bridge and how the ions will basically flow. And it says I can omit the solvent. So I don't need to write down water molecules, but I should use arrows to show how things are moving. Okay, well, just remember for potassium nitrate, it's created by, or it's made of these ions, potassium, which is positive, that's K+, and then nitrate, which is negative, that's NO3, 1-. So we have to think about what I said before, where if this is my anode, and remember that this is breaking down into SN2+, and 2 electrons, but remember these electrons are going to flow again, flow through this galvanic cell. So if the electrons are leaving this anode side, I'm going to have a lot of positive charge built up here. So what I want to do is push negative ions here. Okay, negative ions towards the anode. So that means the negative ion here is nitrate. So I'm going to say nitrate, push it this way, put an arrow, and I'll just label this is going towards anode or oxidation beaker. And then on the cathode side, remember that the electrons, when they eventually get here, they will be reduced by copper ions. So that will make this ion get consumed. So we're kind of losing that positive charge on that side. So this K plus ion is going to go this way towards the cathode or a reduction beaker. Okay, so that's how we answer this galvanic cell problem, and hopefully this video helps you understand the concept better. Please leave any questions you have in the comments, and thank you very much for watching this video. Take care.